All right, so we already looked at these first few slides. I talked a little bit about the format of the exam. There should be no surprises there. And the topics that we're going to cover. And we talked about the labs as well. And I had enough time to talk about topic one, which is kind of a background on water resources and water properties and things like that. And we reviewed the metric system. And we looked at these problems here. So I think this is where we're picking up, and we're going to talk about water chemistry. So if you remember what we talked about water chemistry, one of the big areas that we discussed was we did talk a lot about units of concentration. So things like molarity, percent, parts per million, parts per billion, and mole equivalents. So we're going to do some practice calculations there. This we did not talk about. Sorry about that. That's left over from previous version of the course from years ago. I guess I somehow didn't cut that out. We used to have a lab based on osmotic pressure, and so that was kind of a part of the course, but we kind of moved things around a little bit. Other calculations are going to be based around pH, alkalinity, those kind of things, and then everything else was mostly about things that can be dissolved in water, right? So I think what I'm going to do, I just don't like this red pen. I'm going to change the pen color. How about blue? That's a little nicer. So review units of concentration, pH, and some practice questions for mole equivalent. So let's start here. I'm just looking for my notes, and I can't find my notes. Here's my notes. Okay. So here's got 3 questions here, and I actually broke them down and have a slide for each of them. So let's just take a look at this one. So this one here should be relatively straightforward. This is kind of like Chem 101 stuff. So we're just calculating 3 things: molarity, percent. So usually percent is weight per volume, and parts per million. So let's take a look at molarity first. So molarity, we have to figure out the number of moles. So the number of moles is usually denoted as an N. So number of moles is the number of grams. So 1 gram divided by the molecular mass. So 58.44 grams per mole. So so in this case, you can see that the grams are going to cancel out and the moles are going to go on top. So the answer is 0.017 moles. And the concentration, of course, is going to be the number of moles per volume. In this case, it's 1 liter. So that's pretty easy. 0.017 moles per 1 liter. So I'll just call it like that. And don't forget that moles per liter is also represented by the big M. That's same as moles per liter. So that's molarity. So percent is usually what we do is the mass of the solute divided by the volume of the solution in milliliters. So volume solution, and this is milliliters, and the mass is in grams. It's the same units, and then times 100 to give us a percent. So this is 58.44 divided by 1,000 milliliters times 100. So I don't have that one already pre-calculated, but I can punch that in my calculator. 58 point, my calculator's giving me some problems. There we go, 58.44. I gotta press hard on those buttons. And okay, hold on, I just messed that up now. Oh, my calculator is really killing me here. It's an old one, I haven't used this one in a while. So it's basically 58.44 divided by 10. I should have been able to do in my head. So 5.844%. All right, so just enough space. Just enough space for parts per million, right? So remember, parts per million is milligrams per liter. So we have the number of grams, which is 58.44. So multiply that by 1,000, so that's 58,440 milligrams. So this is actually really, really high for parts per million. And you can do that with sodium chloride pretty easily. And it's per 1 liter. So that would be 58,440 parts per million. Okay, so that was just a quick kind of review of how to do those. Hopefully that wasn't too difficult.
Hey, Blaine. For significant digits, probably just keep the 3 then throughout the whole, like all the calculations.
Yeah, I mean, I don't really necessarily watch significant digits too carefully. Always carry a couple extra more than you'd think. So like in this case here, we have 58.44. So usually what I do is carry a couple past the decimal place.
Yeah.
And usually that is safe enough. Like in this case here, the answer, I wouldn't go more than, 5.84 would be technically correct, right? But since I have them all, I'm writing them all down.
Okay.
It's always safer to have a couple extra than not enough, right?
Yeah.
All right, so B, it says, given the following molecular weights, determine the concentrations of each in parts per million. Wait a second, we did that already, didn't we? Oh, I see. Okay, yeah. So this is asking for each of these, right? So I'm actually going to. So in this case here, I'm going to skip this one. I'm pretty sure people are pretty decent with parts per million, but what I want to do is get to this mill equivalent stuff. If you have some problems with that, let me know. Like I said, the answers are in the notes section of the PowerPoint. So let's talk about determining mill equivalents per liter. Okay, so remember to determine mill equivalents per liter. So mill equivalent per liter. Okay, so in order to do that, we take the milligrams per liter and we divide it by the equivalent weight. Okay, so sodium, do that one first. And okay, so the concentration is 393 milligrams per liter divided by the equivalent weight, which is 20 milligrams per mill equivalent. There we go. Sorry for the messy handwriting, folks. So 393 divided by 23 is basically 17 mill equivalents per liter. We do the same thing for chloride. So I'm not going to write all the units this time, but it's basically 603 divided by 35.5. And we're also going to get 17 mill equivalents per liter. So one reason why I did this is to just show you something. Remember, we started off with sodium chloride. So for every sodium ion, there should be one chloride ion. And so the fact that we get the same number in the end confirms that, because remember that mill equivalents, what it is basically the number of moles. And it, although it's taken the valence into effect, but in this case, the valence is 1 for each of these, right? And milli is 1/1000. So this is basically 0.017 moles per liter is what we're looking at. And that's actually what we calculated, remember, in the molarity of this. So just showing you how all these numbers kind of work out in the end. So make sure you know this formula. Like I said, you are definitely going to have to use this one and convert between mill equivalents per liter and milligrams per liter. You'll be given your equivalent weights. You won't have to calculate those at all. So let's just take a side step where I'm going to get to hardness and alkalinity in a couple minutes. Want to just talk about pH and acidity. So I have some questions here regarding pH and acidity. So let's take a look at A here first. So A says calculate the pH of the following. So basically you got to just remember the pH formula. which is pH equals minus log H positive. So we'll call this one A. A, pH equals minus log 0.001. If you know how logs work, that should be a pretty easy one, because that's this is going to be minus log 10 to the minus 3. And the way logs work is you basically take that exponent, and there's a negative out front. So in the end, the answer for this is just going to be 3. It's a pH of 3. And if you take a look, this here is the same number. So same thing, you got to punch that in your calculator and you get a pH equals 3. Or if you just know how logs work. Now this one here, the reason why I put this one here, I wanted to show you this is a little bit different. You can see we have 0.01, 0.03. So that is actually going to give us a different number because we're actually looking at the exponent. And so this one here, I can't do in my head. I have to throw into my calculator. And so when I do that, I know it's going to be close to 3 because it has basically 3 decimal places over. And when I punch that into my calculator, I get 2.5. So if you do have any difficulties with your calculator, let me know. Some of them are trickier than others in terms of all the log and inverse log stuff. And that's where sometimes people get a little mixed up. I'm very familiar with my calculator. Always takes me a little bit of time to figure out other people's calculators. So B, it says which is more acidic. So this one here, we're already given the pH for vinegar. That's 2.8. So let's take a look at gastric juice. Remember, pH equals minus log H positive. And this one here, because it's a 1, I know my pH is actually, when I punch that in, it's going to be, H is going to be 2. So which is more acidic, 2 or 2.8? How does the pH scale work?
2 is more acidic, I think.
Yeah.
Yeah.
Okay. So like I said, this is pretty straightforward, but it's important to know that. And you're gonna talk about pH more in organic chemistry too. So you have lots to look forward to. I know everyone's just really looking forward to organic chemistry. I used to teach organic chemistry, and it's I really enjoy that course. It's a lot more interesting to teach than to take, though. I'll just say that. First time through can be a little weird when you're learning a lot of stuff for the first time. Okay, so this one here is asking us to go the other way around. So if you remember our pH formula, so swapping this around is the hard thing. And sometimes it's hard depending on your calculator to figure out how to work this. But the way this works is that when we flip this around, pH equals 10, or H positive concentration equals 10 to the minus pH. So I actually, in my calculator, there's 2 different ways to do this. So in this case here, H positive equals 10 to the minus 5. Actually, in that case, that one's easy because that already gave me the number. But in my calculator, there's a way to put in minus 5, and then I can go, which button do I use? I have one here, or actually I have a button, sorry, that's 10 to the X. So I can just use that button, but not every calculator has that one. So this is 10 to the minus 5. There's hydrogen concentration. Don't forget your units. Always remember your units. If you don't have your units on things, you can lose marks for that. All right, so one more for pH. It says which of the following is acidic, which is alkaline, etc. Okay, so hopefully everyone remembers this one. C's. Hopefully everyone remembers that carbon dioxide is acidic. Remember, it combines with water and it makes carbonic acid. So this is acidic. Baking soda. So baking soda is sodium bicarbonate. Any thoughts on that one?
I think it's basic.
Yeah, so remember our carbonate and bicarbonate. These are the things that we consider when we're talking about alkalinity. So both of these are actually alkaline. And those are the compounds we're most concerned about when we're talking about alkalinity. And the last one, sodium chloride salt, is neither. It's basically neutral. We don't have anything there that's really making it acidic or basic in it. So not trying to be a trick question, but just throwing that in there to make a point that not everything is going to be acidic or basic, but a lot of things are. Okay, so let's get down to this milliequivalent stuff here. So I want to review mostly hardness and alkalinity here. So like I said, on the final exam, you're going to have a water analysis question, kind of like, I think that was test number 2. And it'll be most of the same questions, not all the same ones. I'll just tell you one thing. I'm not going to make you make a bar graph on the final exam. I think everybody showed me they can do that already, so I don't have a problem with not doing that one again. But most of the questions will be the same. So you end up with a table, something like this. The water analysis, usually we separate out the cations over here and the anions, and then usually you have the equivalent weight for calcium carbonate as well. So first thing to do is always you're going to calculate the milliequivalents per liter, and remember that formula. You're basically taking the milligrams per liter and you're dividing it by the equivalent weight. You can't spell. I don't know if you guys are like this. I just can't spell when I'm talking. I'm not sure why. Just that part of the brain that's using one part of the language and then trying to use the other part of the brain using language, it totally gets cross-wired. Could be an age thing. I'm super old now, right? But yeah, so you're just dividing, 67 divided by 20 is 3.35, 18 divided by 12.2, and so on. So that's part of the analysis. Like I said, I'm not going to ask you to do this, but I might ask you other questions about the analysis. If you recall, around test 2, we were talking about things like what we're talking about, the balance error, and you may have to explain why the anions and the cations are not equivalent. So usually I'll ask you at least one question along that order. What I do want to do though is just go through a sample calculation of the hardness and the alkalinity to remind you how to do that. So let's look at hardness first. So hardness, we are looking at calcium and magnesium. Sometimes there are other ions that are multivalent cations, like iron, but usually they're so small. Like you'll have 67 milligrams per liter of calcium and 18 milligrams per liter of magnesium and 0.1 milligrams of iron. So in the end, it usually doesn't make much of a difference. Not saying never, but every time I've seen it, it's never made any difference whatsoever. It's kind of in the second decimal point or maybe in the first decimal point. So remember, to calculate hardness, basically what we need to do, step 1 is we need to convert to milliequivalents per liter. And step 1 is we add the basically we add the number of moles, which is the milliequivalents per liter of calcium and magnesium. Okay, so that's 3.35 plus 1.48. And what does that give me? 4.83 milliequivalents per liter. Okay, so that's step 1. Step 2 is basically we are converting that to the proper units. So step 2 is convert to milligrams per liter of calcium carbonate. So the way we do that is we basically take our number of moles of hardness and we multiply that by the equivalent weight of calcium carbonate, which I cut off. It's 50 though, so 50 milligrams per milliequivalent. And so my answer here is 241.5 milligrams per liter calcium carbonate. So don't forget those units. They include milligrams per liter and calcium carbonate. And like I said, that's kind of just stuck there for historical reasons, and that is the way that we decided to do it as a human species, I guess. So remember hardness, these two things, okay? These two things are very important for hardness. Every once in a while, some people do get hardness and alkalinity mixed up, but I think most people were in decent shape at the test. So alkalinity, we're looking at carbonate and bicarbonate. So it's very similar steps. Step one is we add up the alkalinity, and we basically add up the bicarbonate and the carbonate. I guess that's a 2 negative. There we go. So this equals 2.95 plus 0.50 milliequivalents per liter. And that gives me 3.45 milliequivalents per liter. And then step 2, let's convert to milligrams per liter calcium carbonate. So we take 3.45 milliequivalents per liter times 50. And that's 50 milligrams per milliequivalent. So, you know, it's always a good idea to write out the units, and then you can see that things are working out right. You can see 3.45 milliequivalents per liter, and milliequivalents is down here. And so that cancels out, and it's going to give me milligrams per liter. So just squeezing that in there at the bottom, 172.5 milligrams per liter calcium carbonate. Maybe I got to go widescreen with this to fit everything in next time.
Sorry, Blaine, that was finding the alkalinity?
Yes. Yeah.
Okay.
So I have it bolded right here. Yeah.
Thanks.
Okay, so hopefully that is pretty straightforward. Like I said, I think based on what I saw on the test for that, I didn't have too many concerns. Most people kind of had most of the steps. There were 1 or 2 people that had funny answers because they, I think they rounded off too early. You know, like they used 2.9 or something instead like that. And then the answer ends up being 180 in the end or something like that. But I think that part of the course, I think most people were in good shape. Just make sure you go back and review some of those problems. So topic 3, we're talking about waterborne diseases and other biological effects. So things like algal blooms, and we talked a little bit about biochemical oxygen demand. So with the diseases, make sure that you do go through and know some of them. Usually I'm gonna have some questions about it. I think, I'm trying to remember what I had on the test. I think on the test I had something about, I can't remember if this is the test or if this is a past exam, but one of the types of questions that I might ask is, you know, list 3 organisms that may have detrimental effects to water and explain what those effects are, right? So if you're going to explain some of these biological organisms, give me their names, you know, hepatitis A or something like that, and tell me what it does. You can, you know, algae would fit into that category too, because in that case, in that type of question, I wasn't necessarily asking for diseases, but make sure that you know a few of them. You know, maybe one of each category, you know, bacteria, virus, protist, something like that. And we also did have the swimmer's itch as well in there, which is kind of, I guess it's a disease. It's just something that's a little bit different because you're not drinking it, right? So I thought I had a sample question for biochemical oxygen demand, but I guess I don't see it in there. I wonder if I forgot to do that. I meant to do that. I'm just looking at my notes here. Apologies for that. Okay, so I guess I don't have that, or actually I do have this, but actually I have it at the end when I talk about the labs. So we'll get there in a bit here. So topic 4 was a really short topic, mostly talking about laboratory stuff and field sampling, and was really designed to help you a little bit with understanding spectroscopy in the lab and to give you kind of an idea of what field sampling looks like. So some things to know about, you know, like I said, there's not necessarily a lot of standard procedures, although one standard procedure that you should know a little bit about, which I didn't have time to put on the test. So you can certainly expect to see it in the final exam it's going to ask you something about this clean hands, dirty hands thing. So make sure you look that up because like I said, I didn't have time to put it on the test because I just ran out of questions. So I am intending to put it on the final exam. Legal sampling, just know what that is, know what that entails. And I'll come back to spectroscopy at the end here when we talk about the lab stuff. So topic 5, hydraulics. So there were 2 calculations to know for this one. The hydrostatic pressure calculation. So remember that one is pressure equals height times 9.8. Maybe I had it the other way around, 9.8 h, but whatever. And then the continuity equation, which was Q, which is the flow equals V velocity times area. So I have a sample problem for each of those. So here's the first one, and I'm going to just flip to the next slide. It says, what size of pipe is required for this? 35 megaliters per day at 0.2 meters per second. So this is the one that I think half the class got it right, and the other half of the class, there were a couple of minor mistakes. And I was pretty encouraged. Most of the minor mistakes were like things like people just missing a decimal point or something like that. So they had something 10 times bigger than it should have been or whatever. But it's worth it to review these. So let's take a look at this question here. So first, the continuity equation. We already have our Q, right? So we're going to take our equation and we got to flip it around. And what we need to do is find the size of the pipe. Okay, so we need Q over V, like that. And we already have V. So V is right here. I'm going to circle that rather than rewrite it. So I'm going to punch that in and put it in right here, right now. Okay, and so what we need to do is figure out, so I'll just make some space over here. We need to figure out Q in the proper units. And this is the part that a lot of people get a little bit messed up on. So Q equals 35 megaliters per day. And I'll go through my process about how I convert it. There's ways to skip steps on this, but like I said, I'll show you how I do it. So usually what I do is I write this all in one line, but I kind of put myself in the corner there. So I'm just going to go down the next line. So basically what I wanted to do is convert this to hours. So 1 day is 24 hours. So notice what I did, day is on the bottom in my original value here. So I got to put day on the top. So it's really important you make sure you put things on the proper top or bottom, right? So that things cancel out. Then I need to convert hours into seconds. So you can convert to minutes first if you like, but I'm just converting directly to seconds, so 3,600 seconds. And then the other thing to convert is my megaliters to cubic meters. So there's 2 ways to do it. I can convert to liters and then cubic meters first, or I can do this in one step. And I know that basically, sorry, my brain just had a little blip here. Megaliters is on the top, so I need cubic meters on the top and megaliters on the bottom. So 1 megaliter is 1,000 cubic meters. So like I said, if you want to do that in more steps, you can convert to from hours to minutes and then minutes to seconds. And if you want to convert the liters in more steps, you can convert from megaliters to liters. Remember, 1 megaliter is 1,000 liters. And then 1,000 liters is 1 cubic meter. But so I made that a little bit more of a shorter conversion. And whichever works for you best. So let me just look at this. So my days cancel out. I'm going to cancel out all my units. My hours cancel out. So that works out. I'm going to get seconds. And then my megaliters cancel out and I'm going to get cubic meters. So my Q, when I punch all this in, is 0.4 cubic meters per second. So I can put that back into my original equation. So 0.4 cubic meters per second. So you notice I tried to make the math work out really nice. Sometimes it's nice when things work out well. All right, so area is 0.4 okay, I rewrote that, sorry, is 0.4 divided by 0.2, it's 2. And this would be square meters, right? Because we have the cubic meters divided by meters. And so that's going to be square meters. So that's looks good because that's what area should be like. So area, remember, is pi r squared. So we're going to manipulate this formula around. And that would means r squared is going to be area divided by pi. So that's 2 meters squared divided by 3.14159 or whatever pi is. And so that means r squared. Now this I need a calculator for. Punch that in and I get 0.64 meters squared. So I need to find r. So I need to take the square root of both of these. So r is 0.8 meters. So remember, diameter is 2 times r. So diameter is 1.6 meters or 160 centimeters. Okay, so be prepared to do one of these types of questions. If you look at all this, there's other variables I could ask you for. I could ask you for the water quantity. So I would give you the size of the pipe and you're going in the other direction. And those are the typical types of questions you're going to see for this one here. Any questions about that one? Like I said, the hardest thing is the metric conversions. I think people sometimes miss something in there. And then of course that affects all the other numbers. So one thing I do tell people is, when you do these calculations, if you get a funny number, sometimes it's an indication you did something wrong. I think I had this question, something like this on a test once, and somebody ended up with their pipe was, I think it was 27 kilometers in diameter. That doesn't make any sense, obviously. So they had forgot to multiply or divide by 1,000 somewhere. All right, so the pressure question. So these ones here, you've got to read the question. And so if you take a look at this, it says we've got a toilet that's 3 meters from the ground level. So feel free to write on the test. If you like to do little doodles, you can draw a little toilet here. Here's my little toilet. Add next to 3 meters, right? That's the advantage of writing tests in person, is you can doodle all over them. If you want to put a little person on the toilet too, you can. Okay, so just ask us to calculate the pressure at A, B, available water pressure at A, B, and S, right? So it's just a height calculation. So pressure, remember, equals 9.8 H. So at A, it's 3 meters. So pressure is 9.8 times 3, whatever that is, 29.4 kilopascals. Okay, and B and S are the same elevation. So we've got 9.8 times 10, because we have 3 plus 7, right? So that is 98 kilopascals. So hopefully that one's relatively straightforward. Usually there's, forgot about that. Usually there's a question about, what happens when the water starts flowing. And then when the water starts flowing, S and B may be at the same elevation, but there's going to be a little friction in the pipe here. And so that's going to actually reduce the pressure a little bit at S. Oh, and I made a slide with extra space so I could answer the question, but I already did it on the previous slide. All right, so the last few units, we're talking about water use and water treatment. So make sure you know a little bit about this, what types of areas use water, a little bit about the breakdown, and a lot of definitions here. This one here is a relatively short unit, but definitely to give you another hint, I know a question I think I asked before was, what are the top 3 water uses in a household? And if you take a look at those charts, there's 3 uses of water that are much larger than the others. So I'm not going to tell you what they are, but spoiler alert, it's not brushing your teeth. That's not the major use of water in your house. Topic 7, water pollution and water quality parameters. So we talked about these things, these MACs. Remember, that's the Canadian version of these things. So MAC is maximum acceptable concentration. MCL, well, what does that stand for again? Maximum concentration limit or something? I can't remember acronyms. I'm never good at acronyms. So review this one here. Usually I'm going to throw in some sort of calculation that might look something like this, just to see that you actually understand the implications of what these are. So I think I have this on the next slide, so we can take a look at that. So here's a case of where I have microliters, and I think I had mentioned before, I didn't expect you to necessarily remember what micro was. So I'm gonna tell you now, and I'll make sure I have that on the exam if I have it. So a micro is 10 to the minus 6, right? So 1 microliter is 10 to the minus 6 liters. So it's 1/1,000,000th. So hopefully that will help us with the calculation. There's another calculation that I know, and I'm going to convert this a little slower. So 1 microliter, if it's 1/1,000,000th of a liter, it's 1/1000th of a milliliter. So that is where the route I'm going to go. 1/1000th of a milliliter, so 0.01 milliliters. Okay, and if you remember the conversion, a milliliter is equivalent to 1 gram. So that's what we're trying to do. We're trying to get to milligrams per liter, right? So 1 gram is 1,000 milligrams. So I multiply that by 1,000, and that is actually 1 milligram. So there's an easy conversion to remember. Maybe is 1 microliter is 1 milligram. So in this case here, we have 0.00005 microliters per liter. So we can say that 0.000, it's a lot of zeros to remember. You can use scientific notation. I just tend to not necessarily use it all the time because I know some people, they will mess up with it once in a while. So microliters per liter is basically 0.00005 milligrams per liter. So this is a lot lower, right? So this is therefore acceptable. So when you answer these kind of questions, they're usually worth 2 or 3 marks based on how much work you have to do. Make sure you answer both parts. Make sure you show your calculations, and make sure you actually answer the question, the yes or no part here at the end. All right, topic 8, drinking water processing. So I think I had mentioned in class, what I'm going to do is basically ask you to, I think I have some pictures here. Yeah, there we go. There's the picture I was looking for. I'm going to ask you, one of the questions at the very end is going to ask you to either give an overview of drinking water processing or wastewater processing. Right, so I think I told you this before. So it's going to be a big, like 10-mark question or something like that. I haven't decided exactly how many marks it's worth yet. And so what I want you to do is basically make a flow chart or a diagram. Your diagram could look something like this, and then discuss the major processes, right? So if you take a look, this is drinking water processing. So, you know, what's going on here at number 1? So number 1, we have the coagulation, right? So this is coagulation and flocculation. So you want to basically, you know, label that and then give a description about, you know, what is going on there, right? Don't just tell me that this is the clarification step. What I want you to do is tell me what is going on there. Step number 2 is clarification, by the way, or sedimentation, and you can use either word. This is filtration. So like I said, you know, give a description about these things. So make sure you know at least are prepared to describe one of the processes, either drinking water or wastewater treatment in detail and in writing. And the other one is going to be in other parts of the test anyway. So you pretty much should be prepared to describe both of them. Number 4, this is probably some sort of disinfection. Number 5 is storage in a water tower. So fair enough. Any questions about that? So there were a lot of secondary treatments that we also discussed, things that aren't necessarily done everywhere. I like this diagram here because it's kind of showing the basics. You know, things like fluoridation. Fluoridation is not necessarily done in all water treatment plants, but you should definitely know a little bit about it. You know, we talked about some other techniques like filtration, reverse osmosis, and those are all important techniques to know a little bit about. So topic 9 was on wastewater and mostly about characteristics and collection. And one of the main things to know a little bit about was that a lot of places have separate systems for dealing with stormwater and sanitary sewer, right? So make sure you know what the difference is between those things. I was talking to a city worker actually about a week ago, and I learned that what was he saying? I actually asked him the question. I said, you know, when they rip up parts of the city, are they trying to upgrade these systems? And he said it's just not economically feasible, you know, to reroute the entire sewage system. So places that are combined sewer versus places that are separate sewer, they're going to stay the way they are basically for all of time unless the entire city is leveled. So I guess I just kind of talked about this already. Remember, I'm showing you this. This is the sanitary sewer. I don't know why they use the word sanitary. Maybe it's meaning that it's kept separate from the environment, and using that kind of way to use the word sanitary. And then storm sewers, you can see over here, are separate and usually go into these retention ponds where available anyway. So topic 10 was on wastewater processing. And so remember, this was a little different. And we broke it down into different stages. So we had primary, secondary, tertiary, and solids treatment. I think I have a little picture or a flow chart here somewhere. I thought I had a picture, but maybe I don't. Yeah, I have this matching question I'll look at in a minute. So like I said, be prepared to you know, discuss this one as well and what the difference is between all of those different stages. And I did have some notes on the facility here in town. Because we didn't go on the field trip, I won't necessarily ask you steps that are directly related to what's going on in Fort McMurray, but it is part of the notes. So there might be one multiple choice or something like that in there that may ask you about what's going on in Fort McMurray. So here's kind of a little matching question we can work through. So remember that primary and preliminary treatment, what that is. That's kind of the initial screening and filtering and sedimentation that goes on right at the beginning. So that would be here, obviously. And there are some primary clarifiers that are basically sedimentation tanks that the water gets to go through right at the very, very beginning. But that's usually it for the primary. Like I said, it's just very basic screenings and grit removal and allowing things to settle out right away. Secondary treatment, this is the big part. This is a lot of the biological treatment. And so what does this include? This includes activated sludge. So remember, activated means that we're adding basically air, oxygen being kind of the important part of that. Sometimes these things are also called bioreactors, although often when we say bioreactor, we're usually referring to the anaerobic systems. And so I'll say that no O2. And those are really important for areas with lots of cellulose. So farming areas usually have much more extensive bioreactors. We have a kind of small one. And I think the sludge often ends up going there in the end to try to break it down further. Some places have trickling filters. So if you remember what trickling filters are, they're basically giant gravel beds. And these giant gravel beds, the water is sprayed over top. And as it sort of trickles through, You know, it's the water and the organics in the water are broken down by organisms that that are in the biofilms that are on the gravel. Let's see here. Anything else here? Yes, one more. Stabilization ponds. So these are often called lagoons. Kind of prefer the word stabilization pond. Lagoon to me makes me think of this you know, beautiful swamp out in the middle of the forest, but rather than a bunch of sewage. But this is kind of the same idea as the activated sludges, except for it's just allowing natural sunlight and water to and air to get in there. And so they're usually a little bit slower and for smaller municipalities. So tertiary treatment is kind of above and beyond this, and this is where we're getting to places are starting to add tertiary treatment. The big one that is being done in a lot of places, partly because it doesn't take a lot of capital to do so, is adding UV treatment. So this is a big one to know for tertiary treatment. But we're starting to see some places are adding this ultrafiltration. I mentioned that as something that's being done in Edmonton. And apparently some places are doing chlorination, and I'm not aware of any place in Canada that does that, but it's possible it's done somewhere. So that leads to solids treatment, and what's left for solids treatment? Composting, maybe we could add landfill, because in some places that's what the ultimate fate of their composting or their solids treatment is. Okay, so hopefully, like I said, you can remember what all these things are, and you'll be expected to tell me a little bit about these things on the final exam. All right, so that leaves us with air quality. So we spent probably the most amount of time over here on CO2. There's no calculations I expect you to do for the air quality section. So expect some short answer, multiple choice set questions around these things, mostly around CO2. You know, this is a good question here, asking you what that's all about. You know, it really was basically a lecture and a half, so it won't be a huge part of the course, but maybe in the future it'll be expanded. I'm not sure yet. So make sure you know what this is. So we did talk about that, and that's probably one of the most important things to know a little bit about. Okay, so let's talk about the labs. I wanted to do some sample calculations around the labs as well. So let's kind of review what we did. So lab one, we had, hold on a second here, what happened? What's going on? There we go. Okay, I see I have two parts, two questions. So lab one, if you remember, this very first lab, you were doing a titration. And there were two parts to lab A, right? So the first part is you had to standardize some EDTA, right? And so the way that the EDTA was standardized, and actually, hold on, let me just read the question, getting ahead of myself. So EDTA solution is this much, right? So remember, we're basically looking at one-to-one reaction of EDTA with calcium, okay? And then the two things react and they make a compound in the end, which was detectable by titration because it changed color. So here's some information. We have 5.26 mils of EDTA solution, and that was used to titrate 100 mils of river water, okay? So that's the first place we're gonna start. So remember that basically, the way that what this means is that we're looking at the number of moles of EDTA is going to be equivalent to the number of moles of hardness in the water. So this is a good place to start. Okay, so how do we figure out the number of moles of EDTA? It's basically concentration times volume. And we can do the same thing with the water sample. So concentration, we'll call it H for hardness, times the volume of hardness. Okay, so I'm just going to punch in these numbers here. So concentration of the EDTA is 0.095 moles per liter. And the volume is in milliliters. So got to convert that to liters. So 0.00526 liters. And then we don't have the concentration of the hardness. So that's actually what we're calculating. Concentration of hardness times the volume, which is 100 milliliters. So that's 0.1 liters. So by the way, in this kind of thing, this is just kind of an aside in terms of the math, what is going on here. So notice I converted my milliliters to liters. Technically at this point, that wasn't necessary because I would have had, I've had to do the same thing to both sides. Both sides I've divided by 1,000. So if you ever see that, as long as they're the same units, you don't necessarily have to convert because they're going to cancel out in the end. So let's figure out the concentration of hardness. I gotta basically punch 0.095 times 0.00526 in my calculator, and then I'm going to divide that by 0.1. So I'm not going to show that. I'm just going to go right to the answer, and that is 0.05 moles per liter of hardness. So that's going to be calcium and magnesium, right? So the last thing is we have to convert it to milligrams per liter of calcium carbonate, and we have the molar mass. So remember to convert to, I'm going to write this down. So therefore, we're going to convert to milligrams per liter calcium carbonate. So what we're going to do is basically take our concentration, 0.05 moles per liter, and basically we're converting to milligrams, right? So we're going to multiply this by our molecular weight, so 100.1, I think it was, yeah, grams per mole. So that's going to convert this to grams per liter, and then I need to convert it to milligrams, so 1,000 milligrams per gram, and just enough room to squeeze the answer in at the bottom. So the answer here is 500 milligrams per liter calcium carbonate. Okay, so I don't know how easy or hard that is for you folks. If you've done a lot of chemistry like I have, it's just kind of second nature to think about converting between moles and concentration and volume and all those kind of things. And that's basically what I'm doing here. So remember, this formula, right? The number of moles is concentration times volume, right? And that's kind of the basis of this whole thing. And at titration, you have two things reacting, and so the number of moles are equivalent. The complicated part of this is in the end, I had to do a second conversion because I had to convert it to moles per liter of hardness, 2 milligrams per liter of calcium carbonate. So a second conversion there at the end because I wanted the right units. So this is the kind of question that I might ask, and then I might ask you in the end, is the water hard, and give you one of those scales, and you have to kind of answer yes or no or something like that, right? Or tell me where it falls on the hardness scale. So that was part A of lab 1. If you remember, part B of lab 1 was basically using the pH meter. So you can see it's saying, hey, what are two ways of measuring pH? So if you remember lab 1, we had a pH meter, and we also had the pH paper. You could also say that we can use indicators. Okay, so we've already done these kind of calculations, figuring out pH and hydrogen ion concentration. So I'm not going to do that right now. All right, lab 2 was on biochemical oxygen demand. And so there's a couple of questions here. It says, first, why did blowing through a straw change the color of the solution? So if you remember, what we were trying to do is change the pH of the solution. Of course, in the air coming out of your lungs, there is CO2. And we all know that CO2 is going to make the water acidic by adding carbonic acid. And color of the solution changed because we had a color indicator in there, and it was phenol red. And so phenol red goes from like a pinkish reddish color to a yellow color in acidic conditions. Second part of the question, how did Elodea change the color? So Elodea is an aquatic plant, and aquatic plants consume CO2. So that's part of photosynthesis. So I think I asked this question before. I can't remember if it was on the test or not, or whether it was a different year. But lots of people are telling me that photosynthesis makes oxygen, and that's great. We love oxygen, but oxygen doesn't do anything to the pH. So that's not the answer. The answer is that photosynthesis consumes carbon dioxide, and so that's removing acid from the solution, technically, because of course the carbonic acid is going to get converted to CO2. Second part of the question, I think, do I have an extra slide on this? Yes, I do. There we go. Let's talk about the BOD, okay? So biochemical oxygen demand. So remember BOD5, what the formula for that is. So BOD5, it's a 5-day measurement from day 1 or day 0 and day 5. And the way this works is basically we take our dissolved oxygen first reading, so DO1 we'll call that. And then we subtract DO2. And this is multiplied by the total volume divided by the sample volume. So there's a couple of different ways. I think I showed you that formula, but that's the way I remember the formula. So now I just need to read the question. And so it says here we have, so let's see here, our first reading is 13.45. Okay, so 13.45. And after 5 days, it was 1.45. And those are, of course, in milligrams per liter. And my total volume, I'm reading the question, my total volume is 10 plus 40. So that's 50 mils. And the amount of the actual sample is only 10 mils. So 10 mils. So punch that into my handy dandy calculator, and I'm getting 60 milligrams per liter. So that's actually not too bad for water. Pristine water is going to be like, very low, like 1. Something like that, but really contaminated wastewater is going to be in the hundreds. So that's really not too contaminated. Is there a question?
Yes, Blaine.
Mm-hmm.
What if there's a situation where DO2 is bigger than DO1?
That does happen sometimes. I think somebody was asking me about that in the actual lab. I think there was at least one group that had that happen. Was that your group?
I think.
Yeah, so that does happen once in a while. And usually that's a little bit of either 2 reasons why that happens. One is sometimes with pristine water and the issue with the dissolved oxygen probes. So they're not exactly, sometimes they're quite not very accurate, right? So let's say you measure your water and the dissolved oxygen is, let's say it's, you measure it and it's, let's say 12, and then the second time it's 12.5. It means the water is pretty clean already, and there's that amount of error in the dissolved oxygen probe. The other reason is sometimes this happens is that I think the one water sample we had algae in it, and algae, of course, undergoes photosynthesis, and it can create a little bit of oxygen even in the dark. There's still a little bit of photosynthesis kind of happening after. For a few minutes after you put it in the dark, but that's usually the case. It's kind of like an error in there, and it happens, but good question. All right, so lab 3 was the water analysis. So if you remember lab 3, that was the big one that you did the formal report on. And so it was measuring dissolved ions and conductivity, a bunch of other things. And so one of the calculations you had to do for that was basically convert from conductivity to milligrams per liter, right? And there's different conversion numbers for this. kind of basically, depending on the manufacturer, sometimes they give a different recommendation. It's gonna actually be very different for every water source, but so it's a bit of an approximation. So this one is saying basically that 100 microsiemens per centimeter is 62 part per million. And so we're just converting to parts per million or milligrams per liter. So the way that I do this one here is I do a cross multiplication kind of thing, right? So if you take a look, I can do this kind of thing. So I have 488 microsiemens per centimeter, and my conversion is 100 microsiemens per centimeter. And I'm calculating for X, which is my my parts per million. And so there's my conversion, 62 parts per million per 100. So that's usually how I do this problem. There's a couple of different ways areas to start, but I find this is the easiest way to do it in my mind. And then it's just a matter of punching this into the calculator. So I'm taking 488 divided by 100 and multiplying by 62. So I got 303 parts per million. And of course, parts per million is equivalent to milligrams per liter. All right, so lab 4. Explain how to test pH using pH paper. Oh, I meant to put that for lab 1. So like I said, I will be having a few questions around the labs. So do make sure you do review them. And if you were doing the labs and you're diligent in helping your partner, it shouldn't be too much of an issue for some of these types of questions. So question 4, I wanted to kind of review a little bit about spectroscopy and how that worked. And if you remember with spectroscopy, we had 2 steps to this, right? Step 1, we were basically making some stock solutions and then measuring the absorbance. So making the solutions were a few steps. I think you had about 4 or 5 things to add to each tube to, and you're trying to do that relatively precisely. And so what you're doing is basically making a plot of your standards and your absorbance. And then you're using that plot to figure out the concentration of your well water. Now I'm just trying to remember whether I have this on the slide. Yeah, I don't have room on the slide to do this so I'm going to make a very, very mini graph up here at the top. So basically what you're doing is you're plotting absorbance on one axis and concentration on the other axis. So my 0, 0, that's an easy one. And then let's see here, I've got absorbance goes up to 0.5. So we'll go 1, 2, 3, 4, 5. So this is 0.5. So basically, and then this goes up to 4. 1, 2, 3, 4. So this is something I could ask you to do on the exam. Now I would have a little piece of graph paper or something like that so that you can make a crude chart. So it's a matter of just plotting this, right? So first one at 1 was 0.14, so roughly here. Second one is at 0.35, so roughly here at 2.5. And at 4, it's 0.56, so something like that. So this is the first step. Step 1 is make a standard curve. Okay, so that's going to be a straight line. Basically connect the dots. Sometimes they're not perfect, but you're trying to make the line of best fit. And then step 2 is you're going to use the curve. I know it's called a curve, but it's really a straight line. I don't know why we use that term. So use graph to determine the unknown. So my unknown, my absorbance is 0.42. So what I'm going to do is basically on my graph, so my unknown is right here somewhere. I'm going to basically draw a line straight over to my curve and then basically straight down, oopsies, straight down to my concentration. So that's probably not too accurate because I made it really small, but somewhere around, let's say 3.7 or something like that. So 3.7 part per million. So sorry, I didn't come prepared to really do that one as much justice as I'd like to do it. If you have any questions about that, let me know. It's worth it to review your lab reports on these. Okay, so the other way you can do this, by the way, is figure out the slope of your curve and use the slope formula to figure out your concentration. So there's two ways to do it. Okay, so we had lab 5 was on flow rates and pressure. Lab 6 was on solids and turbidity. So remember, we had these calculations here: total solids, total suspended solids, and total dissolved solids. And I have a problem for that one here in a moment. And lab 7 was water purification and infiltration. So let's talk about lab 5 for a minute. So lab 5, you had some plots, and so some things that I might ask you is maybe writing a title for the plot, or asking you what kind of information is missing on a plot, or what is going on here, right? So if I take a look at this particular plot here, it's actually telling me two things in terms of the trends, right? Because I have this trend here, right? So that trend is telling me that, okay, as my column height is increasing, so is my flow rate. But I also have the trend between the different curves here, right? So in this case here, it's not giving me any information about the pipe length, but there is a trend with pipe length because we have 3 curves. So I could be asking you something around that kind of thing, like here's some charts, explain them, or maybe what's wrong with them, or maybe, sometimes I maybe add a little twist based on the experiment. So maybe rather than pipe length, I might have, plastic pipe, metal pipe, and clay pipe, and ask you what's going on here. So just be prepared to kind of understand what's going on. So look at your labs and make sure that you look at the comments that Tamar gave you in terms of understanding what is going on. Okay, almost at the end. I know everyone's probably getting tired here. But one more kind of sample problem to go through. And this is the sample problem looking at solids and turbidity. I think, I made some space, but I didn't. So I'm hoping you have this downloaded and somewhere in front of you, because I'm going to just refer back to the data here and remind you of how these calculations work. Okay, so let's take a look at this. So total solids. So total solids, that is where we're drawing down the dish, remember? So total solids basically equals the mass of the dish plus residue minus the mass of the dish initially. We're going to divide that by our volume. We're going to multiply by 1,000 because we want to get milligrams, right? So in this case, there were 2 samples. So I'm just going to do sample 1 for you. Okay, so sample 1, the mass of the dish was 2.55, and the mass of the dish plus the residue is 2.65. So 2.65 grams minus 2.55 grams, and the volume 80 mils. So 0.080 liters, and times 1,000 to get our milligrams. So this one here, I have to punch that in my calculator here. 2.665 divided by 2, or minus 2.55 divided by 0.08, then times 1,000. So this is 1,250 milligrams per liter. So like I said, I'm not going to do sample 2, but you have to do sample 2 as well, and you have to find an average. So I think maybe I had the answers on the previous slide. Let me just take a peek here. So my average for my total solids is going to be 11.25. So I'll come back to that number in a minute. So my total suspended solids, remember we have the mass of the filter plus residue minus the mass of the filter divided by the volume times 1,000. So I'm not going to do this calculation, but basically it's 1.63 minus 1.55 divided by 100 mils total, which is 0.1 liters times 1,000, and that will give me the answer. So I'm doing that 2 times for sample 1 and sample 2, and then I'm going to get my total suspended solids, and that's going to be 100 milligrams per liter. And the last calculation is total dissolved solids. So total dissolved solids is, of course, the total solids minus the total suspended solids. So that's 1125 minus 100. So that's 1,000. Sorry about that. Let me just try that again. That's 1,000 and, oh no, that was right. 1,025 milligrams per liter. So I think people did really well on this question as well on the last test, which is why I don't really want to focus on it too much, because I think people kind of had that straight. It's just a matter of making sure you get the right formulas and again, conversions between things. I think there were a couple of people when they converted from liters to milliliters, or I mean the other way around, milliliters to liters, they missed a decimal place or something like that.
Blake,
Yes?
I have 2 questions. Can we also put our answers as parts per million?
Yeah, milligrams per liter, parts per million, exactly the same thing. So you can use either, it doesn't matter to me. Okay,
and is there a situation where the total suspended solids is bigger than the total solids?
No, and only if there's an error of some sort. Yeah, and that kind of error might happen when you're looking at very, very, very small amounts of solids and you're looking at the limits of the sensitivity of the analytical balances. But total solids is always going to be more because you're capturing everything on the dish, whereas the suspended solids, you're only getting what's caught on the filter. So other things are presumably going through.
Okay.
Did you have 2 questions, or that was both of them?
That was both.
Okay. All right. And this is my last slide. So thanks for coming out. If you have any other questions leading up to this, like I said, you can always book a time with me. I'm pretty available over the next week. I know you have your other exams to deal with, but you can always get a hold of me and we can go through some sample problems and I can try to help you out.